This is trig substitution using completing the square. So you're going to be given something now that's this right here that is not our perfect binomial that we had before. So what we have to do is turn it into that. And that's using completing the square. So if we have this right here, which is x squared minus 8x, what we're going to do is take it and you cut it in half, and then you square it. So we do 1/2 of 8. If it's a minus, we're going to get a minus. And then you take that 4 and you square it, and you get 16. This now gives us a perfect binomial. So if you were to take x minus 4 times x minus 4, and you multiply them out, it's a perfect square. X squared minus 8x plus 16. So it gives us our perfect square. So that pattern again is you just cut it in half, and then you square it. So if you had a fraction, that would just become 5/2, and then squaring it becomes 25/4. So it allows us to take our little binomial we have here and turn it into a perfect square that we're looking for. All right, so we set it up the same way. We take our radical that we know we have to use, and then we're going to modify it into what we want. So we set it up just the way they look up there. So we're going to go x plus 2x, put that in a parenthesis like that. And so that would be our trinomial now. So we're just missing that final term. And then we know we have to make this into a perfect square. So we take whatever we have in the middle there and we cut it in half. So we get plus 1. And then we square it. So that would be plus 1. And you can already see that x plus 2x, x squared plus 2x, let's put that in blue so it matches, x squared plus 2x plus 1 is x plus 1 squared. Now here's the thing, you can't just add numbers to stuff. Everything has to say the same. It has to say equal to what it was before. So if you put a plus 1, all we have to do to counteract that is put a minus 1. And you can see now that 1 minus 1 is 0, so everything works perfectly. So we bring that down. Now you just have to find the trig value that matches. And so having an x plus 1 squared in the front, we know that that has to be secant squared theta minus 1. That's what it has to look like. So that it would become a tangent squared theta, which would become tangent theta. Now that means that if you do our little highlighter here, you can see that our x plus 1 is equal to secant theta. And then that's our substitution now. So dx would just become secant theta tan theta d theta, and we can plug all of this in. So this guy is tangent theta. Our dx is secant theta tangent theta, and we'll do blue. And then our x plus 1 is going to give us secant theta. So plugging all that in, we get tan theta over secant theta, and then we get secant theta tan theta d theta integral. And then we do some canceling, so cancel. Tan squared theta d theta. So we don't have a fraction here, we got rid of it, but tan squared is not integrable the way it is, so let's change it into its Pythagorean identity, which is secant squared theta minus 1 d theta, and there we go, now it is. So this would become tan theta minus theta plus c. And then now all we have to do is replace our theta with an x. So we go back to our triangle, there's theta, and so secant theta is x plus 1, and we just put it over 1. And secant theta is the reciprocal of cosine. So this is really saying cosine theta is 1 over x plus 1. So it's 1 over x plus 1. And then we know that final missing leg is just going to be x squared plus 2x, because just like we've been doing all of them. Now if we plug it in, we know our tan theta would be the square root of x squared plus 2x over 1. So it becomes the square root of x squared plus 2x, don't have to put over 1, minus, and then all we have to do is do the inverse for the secant, plus c. And there we go. All right, so you can see with completing the square, what we're doing again is just converting it into a perfect square. So I'm not going to leave you alone with just one example. Let's try this again. Now this is as bad as they're going to get because it's all messed up. A lot of modifying has to go on with this one. But we start the same way. We write it out and we just keep modifying it until we get that perfect square that we want. So on all of them, if you notice with a perfect square, they all start with positive x squared, positive x squared, positive x squared. So right there, positive x squared. So what we have to do is rearrange it. This would now become x squared plus 4x. Still not good enough. So what we do is we factor out the negative. And now it's positive. That becomes negative 4x, and we put a little parenthesis there. So it's just rewriting it. Now it's just bringing everything down the way we've done it. So we know that has to be an x there, and we know this is half. So minus 2, and then we square it, so plus 4. And then normally you think, oh, this is minus 4 then. Well, that would be wrong. If you distribute that negative, you're going to get a minus 4. Minus 4 is not going to cancel. We need to put a plus there to cancel it. So it becomes a plus 4. Now everything's set up, except we need to now rearrange it into that subtraction that we're always looking for. And there we go. So we are subtracting the perfect square in this case. So we set up the same way. Since it's a minus, we put sine squared theta so that we can get 4 1 minus sine squared theta, which would give us 4 cosine squared theta. Let me bring down the radical now around everything. So it's just replacing over and over again. This is as bad as they're going to get, hopefully. 2 cosine theta is what we would end up with now. And what do we use for our substitution? Well, you just go back to wherever that x minus 2 is, right there, and that becomes this. So we know that x minus 2 is equal to 2 sine theta because x minus 2 squared is equal to 4 sine squared theta. And then we do our integral, our dx equals 2 cosine theta d theta, and we have everything now that we need to plug in except for the values, but we'll come back to those. So that is that. So we'll replace that one, and then we'll use green. So dx becomes that. So we end up with 2 cosine theta, 2 cosine theta d theta. Now we need our integral here. We need our start and stop points. So I'm going to put those in red. So we're going to change our 2 and our 3 from x's into thetas. So if we have x equals 3, that would become x minus 2 equals 2 sine theta. So 3 minus 2 equals 2 sine theta. 1 equals 2 sine theta. That's a half. So theta equals pi over 6. Let me move this down a bit. Perfect. So we get pi over 6 for the 3. Now, x equals 2, that would be 2 minus 2 equals 2 sine theta. That's 0, so I don't have to even solve it. Theta equals 0. So we're going from 0 to pi over 6. And again, we do this instead of waiting to the end because then we don't have to worry about setting up the triangle or anything. All right, so 0 to pi over 6, we put 4 cosine theta squared d theta. Up, there's our square, so we need to turn it into a non-square using our double angle. So that would be 4 over 2, and then it becomes 1 plus cosine 2 theta d theta. So we end up with 2 bracket theta plus 1/2 cosine 2 theta. Sorry, that would become sine now. Pi over 6 and 0. Now we just have to plug them in. We don't have to plug in the 0 because we have a theta and a sine theta. Even with a 2 theta in front of it, it's still going to be 0. So this becomes 2. And then theta would be pi over 6 plus 1/2 sine. And then we would get pi over 3 inside. And then at the end, it's just going to be 2, 0 minus plus 0. So no reason to even deal with that last part. All right, so this becomes pi over 3 plus, and then this is 1/2 times 2 is going to cancel. So we end up with square root of 3 over 2. And there is our answer. And you can check that in your calculator. Plug in the original integral with a math 9, and then plug in our exact value at the end, and you'll see they match. All right, thank you.